Today we are going to talk about parallel iterations, but let me get my Windows set up here first. But first, we need to finish up slides from last week. And we have so many slides to finish up from last week that I'm not sure how far we'll get into this. So the next week, or the next lecture, is on mapping variants. So basically different ways to do mapping functions. And that's like important, but not as important as this stuff. So the way I'm kind of thinking we'll go forward is I'm going to take the time we need today to finish up the stuff from last time, get as far as we can on this today, finish up the rest of these slides on Wednesday, and then we'll just get as far as we can on the modifying or on the mapping variants. And then from there, whatever we don't get to, I would ask that you please review those slides and then ask me any questions if you have any, but we'll just move on from there because we will be the week after this, so next week we'll be moving towards writing functions. Okay, does that make sense? All right, so on to the list columns. If you have your script from last week, you can go ahead and just grab that and work with it. And if not, please just copy this again and get that going. And then give me a thumbs up when you're ready there. It looks like most people. I'll give you another 30 seconds or so. Okay, once you're done with that, please go ahead and copy this too, so that we can get the file parsed and ready to go. And then give me another thumbs up emoji when you get that done. It'll go another 30 seconds or so. Okay, and then we're just going to select the variables that we want, which is going to be the student ID, the grade, year, content. So those are those variables we created in the previous test or previous slide. The test event ID, and then their primary and secondary disability, and then the entry to the WMLE. Okay. Then we talked about this, so I'm just going to sort of go through these slides quickly as a review. All right. So this is not the part that I need you to do anything. So if you're still working on getting set up, that's fine. But pretend we wanted to fit these three models, right? So one with the primary disability predicting their test score, one with their primary and secondary disability, and one with their primary and secondary disability as well as the interaction. Okay, and then we wanted to compare the fit of those various models. So we would first want to make primary and secondary factors, which is what I've done here. And then what the method we had used previous to last week was to use this split function, which is part of base R, where we would take D and split it by a variable, right? And that would give us a list in return where each element of the list is a data frame with just the unique elements of that vector that we have. So just each content area, right? So this is the ELA, then we'd have another one for math, another one for reading, another one for writing, etc. Then we could go ahead and fit those models, but then we would have this list. We would have another list for the model 1, another list for model 2, another list for model 3. And then when we wanted to do these comparisons, we would have all these other objects that we would use, which would probably be other lists to compare these things. And our environment could get pretty cluttered pretty quickly. So an alternative to that is to use list columns. So here we had D, we group by content as if we were going to summarize, but then we just use this function nest. And then we end up with a data frame that looks like this, where each row is just the unique elements of the thing that we've grouped by. And then we have a data column, which is a list, and each element of the list is all the data for the corresponding row. So this is all the data for ELA, this is all the data for math, this is all the data for reading, etc. Okay? So if we actually dig into that list and look at by content data, you will see it looks exactly like that split object. Okay, so it's the same thing, it's just organized in a little bit nicer way. So we can apply map functions to this, just like we did before. And if those return vectors, atomic vectors, then we can actually add them as a column to our data frame, just like this, right? So here I'm using map double to count the number of rows in each data element. Okay, so each data cell, right? If we just use map instead of map double, it returns a list. So in this case, we're doing the exact same thing. Notice the return is just an integer of length 1, but it returns a list, and this list is not really very helpful, right? So this is not nearly as helpful as this, because here we can actually just see those values. It's part of the data frame, whereas here we end up with the list column where it's just not super transparent what is in those things. So basically the idea here is when you can, you want to use these variants like map double and map CHR and whatever to return an atomic vector, because then it just ends up being a new column in your data frame versus a list column. Okay, so list columns are really nice because they're super flexible in the same way that lists are flexible, but they're a little more opaque. And so when you can, you want to avoid them, basically. Okay, so then we went ahead and fit a model. So we said, okay, now we're going to loop through data and we're going to fit our first model. So M1, here's M1, and it's each element is a list, right? Or this is a list where each element is a model. And then we could loop through that model object and extract the coefficients. So we say coef, we get a list of the coefficients. So then we talked about this. We did this little challenge where I said, okay, now we've got all of these coefficients. Can we create a data frame that has just the content, the intercept, and the coefficient for TBI? And so we did that like this, right? Fit the model, extract the coefficients, and then for no disab, we're no disability, right? We're going to loop through coefs and pull the first one, right? Which is the intercept. For TBI, I went ahead and added it to no disab because that would actually give us the mean for TBI. We map double through coefs, and because coefs is a named vector, I can just supply the name of the element I want, which is primary 74. And then I'm just going to select those 3 columns, and we end up with something that looks like this. Okay. So back to our original task that we set out for, if we wanted to fit these 3 models, then we could just continue with our mutate like this. We would say mutate M1, M2, M3, and for each of these, we're mapping through data, and we're just fitting a different model, where .x is a placeholder now for the specific data frame, and we have the tilde, which is, just shortcut syntax to get into the data frame. All right. Then I talked about very quickly a brief foray into parallel iterations, which is actually the topic for today. So if we went mods $M1, right, that would give us this list column in return, which is all the models for M1 across content areas. So if I wanted just ELA, I would say mods $M1, and then double bracket 1 is going to give me just that first element, right? So if I wanted to compare this model with this model, I would do basically the same code, but I'd swap M1 with M2. Okay, so here's these two models. And if I wanted to compare them, I could do that with this ANOVA function. Okay, and then when I say compare, it gives me a test of the residual variance, basically, the change in the residual variance. And we get this p-value, which in this case is saying, yes, the more complex model adding secondary disability significantly reduces the residual sums of squares. Okay, so map2 works just like map, but it takes two vectors. Okay, and again, we'll talk about this more, but basically I'm going to say map2, I'm going to say m1 and m2, apply the function ANOVA. And what that's going to do is it's going to compare this with this and apply the function ANOVA. It's going to compare this with this and apply that ANOVA function, etc. Okay, so it's going to do that. And then we get this comp12 object, which I have here. And this is all the tests between models 1 and 2 across all content areas. Okay, so then that's helpful, but still not terrifically helpful because this is an ANOVA object. And what I really probably want is, information about that ANOVA object. So if we look at that compare object that I did with, which was just that 1 and 2, right, you'll see it has a bunch of stuff. One of them is this p-value. And the p-value is kind of hard to access for a number of reasons. One, this is a non-standard name of an element, and so you have to surround it by backticks if you're going to access it with the $sign. And then the other thing is it's a vector of length 2, and we actually don't want this first thing because that's just a missing value. We want this second thing, right? This second thing is the actual p-value. And so we could do that either like this, compare $sign, and then notice I'm using the backticks because of the non-standard naming convention. And then I put the name of the p-value, and I get the vector back. Or I could say compare double brackets, and then just put it in quotes, and I get the vector back. But again, what I want is actually just that second element. So I would just say 2 with single brackets, because notice now I have a vector, so I would just use single brackets to index that. And that gives me just the p-value in return. Okay, so all this is review from last time, but if any of this is not making sense, please do interrupt me. Okay, any questions so far? Okay, so then if I wanted to pull all the p-values, I could say map double and then comp12, and I could pass it a list. And I could say, give me this thing, right? And then give me the second element out of that. Okay, and that will go in and grab the p-value, that'll return the vector, and then the 2 is saying, give me the second element of the vector. That's fairly complex code, though, and it's not necessarily the most straightforward. So one way you could do this, and you could, use the tilde and .x to maybe make this a little bit more clear. But an alternative way that will, so this is again sort of foreshadowing what's to come, but we could write a function that takes an argument ANOVA ob, okay? And you could call that thing whatever you wanted. But basically, I'm going to take this ANOVA ob, which is just a placeholder for an ANOVA object, and I'm going to pull out the p-value from that. So I'm going to use double brackets and give the name of the p-value thing, and then give me just the second element of that, okay? So that will return just the p-value. So what I can do instead now is say loop through comp12 and extract p. Okay, and you can't see it here. I probably should have done a select so that I could drop some columns here so that we could see that better. But because I've used map double, what I end up with is an actual p-value where you can see the p-value for each of these models, right? It's a vector in return, so it's just a normal column. All right, that's basically as far as we got last time. I introduced this alternative way very, very quickly, but this is kind of where we're going to start today. So, but before we do, are there any questions on any of that part? Okay, so an alternative to this is the new row-wise function that's part of dplyr. This, as I mentioned, is not as general as map, as the map family, as looping, because it will only work for a data frame. Most of the time you can figure out a way to put lists into a data frame, so you have list columns, but not always, right? Or maybe sometimes it's just easier not to. It's easier to not have the overhead of the data frame and you want to just loop through some lists. Or maybe sometimes, like with API calls, it might make more sense to just actually loop through the vector and do the API call versus, you know, creating some data frame that you're going to then use to loop through for all the API calls. All right. But this row-wise function really fundamentally changes the way that the data frame works. All right. So here is an example where I've created this very simple data frame. It looks like this: me, you, x, y, z, and m. What I'm doing here, though, is I'm creating m. Okay. And I'm saying, what's the mean of, and then I have c, x, y, z. Well, what that's going to do is it's going to first combine x, y, and z. So this is going to be one vector that is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, one vector, and then it's going to compute the mean of that. Okay, that's how that works. So even though we would probably expect this not to work like that, we'd probably expect it to give us the mean of this row and the mean of this row, what it's going to do is give us the overall mean instead, which is 3.5. And that's just going to repeat for every single row, no matter how long it is. Okay. Row-wise makes it behave more like you would expect. Okay, so I say df row-wise, and then notice it gives you this little warning that it's a row-wise, well, not warning, but message that this is a row-wise data frame. And then when you compute the mean, then it's going to actually do what you would expect. It will compute the mean for each row. All right. One way to think about row-wise is it's the same basically as if you said group by every single row. Okay, so it's like a group by, but the group by is every row. So like every row is its own group. Okay, so if you want to add something to your row-wise, then when you summarize, it will leave that in there. So I say row-wise name, just like I would say group by name, right? And then when I say summarize, m is equal to mean whatever, name will stay in there. Okay, list columns with row-wise. This is where row-wise gets really interesting and quite powerful. So let's say I have a table here now that is 1, 2, 3, and 4, 6. Okay, so this is just x has this list 1, 2, 3, and 4, 6. So this is all it is, right? If I wanted to compute the length of each of those vectors, the way that we have been doing it, I would take df, I would pass it to mutate, and I would create a new column, which I'm calling L, but you could call whatever. And I'd say map int or map double x, so loop through x, and compute the length. Okay? And this would give me 1, 2, 3. The row-wise version of this exact same thing is to take df, pass it row-wise, and then say mutate L is equal to length of L. So now I don't have to do any looping at all. I just say, what's the length of this thing? And it gives me the actual length. Okay, so that's quite nice. I've avoided looping because I'm using this row-wise operation. With dplyr, you can actually create list columns in a pretty efficient manner with this nest by function. Okay, so what this will do is it will create a list column for each group and then convert the data frame to a row-wise data frame. Okay, so for instance, if I say D and I pipe that to nest by content, it will nest it by content. So I'll get a content column and a data column with the data for all of that. So this is just like saying group by content nest. The only difference is this will also convert it to a row-wise data frame. Okay. So given what we just learned, what I would like you to try to do is nest by content, just like this, and then try to create a new column where you're saying theta is predicted by primary, okay? So do the same thing we've kind of done before, but you do it using this row-wise data frame that you create using nest by rather than using per. Okay, does that make sense? Go ahead and give that a try. The error messages are quite helpful, I think. So if you run into an error, do read those error messages. Okay, give me a thumbs up emoji if you were successful with that. Okay, nobody, apparently. All right, what you have to do here is just wrap it in list, okay? And the error message, if you didn't do this, should have probably prompted you to do this. But basically, it's just going to look like this. All you have to do is you just now refer to the column, okay? So you don't actually have to use any .x or any looping, right? So you do have to wrap it in list, and I'll explain more why in just a second. But you're creating a new object called M1, and you just say lm theta predicted by primary, and data equals data, right? This column. And the reason this works is because it's operating by row, so it's looking at the data column for just this row, okay? Just like a loop would, okay? The reason that you have to wrap it in list is because the return value is a model object, and that doesn't reduce to an atomic vector. So you have to store it as a list column, right? You have to store the result from this operation that you're doing as a list column if you want it to be stored in the data frame. That's the only way that it'll work. And so if you just wrap this operation with list, then you get the same sort of thing that we would have gotten with per. Okay? So challenge 2, now you should have that. Let's see if you can extend it further to extract the coefficients with coef. Okay? And if you're able to do that, try to extend it even further to create a new column, another new column that has just the intersect from those coefficients. Okay? Try to do that. Okay. Give me a thumbs up if you were successful on either part of that. All right, few people this time. That's good. Okay, so we would do it like this. So we have M1, we're saying list, and then we fit the model. Okay. Now in this second one, we are getting a vector in return, but that vector is not of length 1, right? So the only way we can store that is again in a list column. So we have to again use list. Okay. So we say coefs is equal to list, and then we're just going to extract the coefficients from M1, right? So this code right here, coef M1, that's the exact same code that we would write had we created one singular model and we called it M1, right? We would just use coef M1. And so the nice thing about this row-wise operations is that it allows you to write code the same way that you would if you had just a single object, but then you just have to wrap it in list if the output is longer than length 1. Okay. We often want to return atomic vectors, right? And so just like we would use map double or whatever, if the result, like in this case, I'm saying give me just the first element of the coefs, that's going to be the intercept, right? So in this case, the result is an atomic vector. So I don't have to wrap it in list. Okay. I just say coef M1, give me the first element from coef M1. Okay. And then I get the intercept values. Does that make sense? So basically, whether you wrap it in list or not depends on the return value from the operation that you're doing. If it's some complicated thing, then it has to be wrapped in list. If it's an atomic vector, but each atomic vector on each row is longer than length 1, then you have to wrap it in list. Okay. But if you're able to go through each thing and conduct an operation where it's returning a single value each time, then you don't have to wrap it in list. You just write code as you would if that was just a singular object. Okay. All right. So if we wanted to fit all models, we could do it like this, right? I'm calling this mods 2 this time, where I'm saying d nest by and then mutate. And notice this is very similar to the other code. I'm just wrapping it in list and I'm saying go through the data column. Okay, so that should be fairly straightforward. Now, let's say I wanted to look at the R² values for every single model. Okay, the nice thing about this, about these list columns, is that they are just normal data frames. Okay, so we can do all the things to them that we do with normal data frames, including, in this case, pivoting longer. Okay, so I have my mods, I'm saying pivot longer, grab the columns M1 to M3. Now, all of those are list columns, but it doesn't care, right? I'm saying put the names to model and the values to output. So now I have a model, M1, M2, M3, and an output, which is just the actual model itself as a list column. Okay, now from here we can extract the R² from every model, and I'm showing this first with the per version, right? So I'm saying mutate R2 is equal to map double, so I'm going to map through this output list and conduct this operation. Okay, so I'm saying tilde summary.x, where .x is a placeholder for each data frame, and then give me the R² value from that summary. Okay, and then we get the R² for every single model. Again, because we have a normal data frame, from there we could do something like go ahead and move it straight to plotting. So very quickly here, we've fit a bunch of models. We've computed this summary to get an R² for each of them, and now we're plotting them, right? All in succession because we have a data frame, and the tidyverse generally works with data frames really efficiently. Okay. So again, if you contrast this with like having done the same thing, but had them all as different list objects, creating something like this might be fairly difficult. It would take a bit of time to first pull all of that stuff out and build it into a data frame that you want to use to plot. Whereas if you're using list columns, it's really straightforward, right? You can just move the data frame into the structure that you want, pull the things out from all the models, and then plot them. Okay, unnesting, and we're going to get back to nest by and row wise here in just a second. But very often, you want to unnest the data frame that you have. Okay, so these nested data frames are super nice, but at a certain point, you might want to say, okay, now get me out of this nested data frame and just get me back to a normal data frame. So let's say we wanted to plot the coefficients by model. Okay, one thing we could do is we could apply the function broom tidy to every single model, and then we just unnest from there to get all of those coefficients. Okay, so here's an example. I'm pivoting longer just like I did before, but now instead of extracting the R square, what I'm going to do is I'm going to say map through output. Notice I'm not doing map double or anything because broom tidy always returns a data frame. So I'm going to say map through the output and apply the function broom tidy. Okay, this creates this tidied column, which is a list column, and it has the data frame for every model. Okay, now, here's the equivalent version with nest by, right? Or row wise rather. I'm doing the same pivoting, and then I just say move it to row wise. And when I do this now, I just say list broom tidy output. So it helps me avoid the actual loop function, and it helps me not have to use the tilde.x. Okay, but otherwise it's fairly similar. Okay, now we want to actually select just the model, the output, and this is old. So this is all the stuff we did on the previous slide, just old code. Okay, we want to select just the content, the model, and that tidied column, and then we say unnest tidied. Okay, so coming back here, we have this list column, right? And this is a data frame for each content area. Okay, now I'm going to say select just this content column, this model column, and this tidied list column, and then unnest tidied. Okay, and what we end up with is something that looks like this. So we have the content and the model, and notice these are repeating now a bunch, and then we get just the tidied data frame for every model. Okay, and so what that allows us to do is do things like plotting, right? So we're looking at how the primary coefficients change. So basically, I'm saying just give me the coefficients from the first model, and then I'm saying in tidied, filter where the term is in toplot. Okay, so toplot is just the names of those coefficients. I know that's kind of confusing, but basically, when we think about our models, we have primary disability, secondary disability, and then the interaction between those two things. This code on the next slide is to say, okay, where the term is equal to just this thing, right? So either the intercept, primary 10, primary 20, all the way up to primary 90. And then if it's anything else, it's going to be dropped from the model. Okay. Then I'm saying put the estimate on the x-axis, the term on the y-axis, set the color to the model, geom point, change the color of the points, and then pass it wrap. So we get something that looks like this. Okay. And what's neat here, again, is just that we're comparing across all of these models across different content areas and everything. And again, it's like fairly quick, right? Okay, last bit. This whole time that we've been doing this, in some ways we've been running the wrong model, right? It depends on what your purpose is and whatever. But we forgot about grade, right? We've been running separate models by content area, but not by grade. And in most of the work that I would do for these data specifically, the analyses would need to be conducted separately by content area and grade because they are statewide testing stuff, okay? So we've done all of this work now, and we realize that we've been fitting the wrong model the whole time. Well, the nice thing about this is all we have to do is change our group by. So we have D, instead of grouping by content, we now group by content and grade, and then nest. And now our nested data frame looks like this, but everything else is the exact same. Okay, we still have this data column. We're just going to loop through that, and everything else is exactly the same. Okay, we fit our models, we look at our R square, and then we plot, and it now looks like this. So I changed the plotting code slightly so that it would use facet grid by grade as well as content area. Okay, so final summary here for list columns. They're super powerful and really flexible, and they really help you stay organized. All right, but in addition to helping you stay organized, they help you use all the tools that you already know from previous courses for data wrangling with data frames, because most of the work that we do focuses on data frames, right? And so putting a list in a list column helps you get back to those functions that we're used to with dplyr, okay? You can also use the new dplyr row-wise approach, which will help you avoid actually using the loop, okay? One really important thing that I haven't mentioned about row-wise yet, though, is if you do enter into a row-wise data frame, right? So you pass your data frame to row-wise, you're going to want to make sure that you then pass it to ungroup when you're done, okay? Otherwise, it's going to continue to operate in that row-wise way that you probably don't want, okay? And again, as I said before, row-wise really is equivalent to grouping the data frame using group by, but for every row. Each row is its own group, okay? So I am asking you to learn both. In some ways, I think the new row-wise approach is better because it helps you avoid having to learn about loops, but I'm asking you to learn about loops anyway, because they work on everything, including not data frames. And just from a sort of like general programming sort of perspective, loops are incredibly important. Most of what you do, most of what the tidyverse is essentially wrappers around different functions to help you avoid having to do loops, okay? So if you're going to get to the point where you're writing your own R packages or you're solving really complex problems for people with their data, then you're almost guaranteed going to have to write a loop at some point. So that's what we've really been focusing on. Row-wise is one way to do those loops, and they are looping still. It's just a slightly different way to do it. Okay? Any questions on that, on any of that? Okay, so again, if you look at the homework, you will see I am asking you twice to do the same thing, once with per and once with row-wise. Okay, so parallel mapping. Today we're going to talk about map2 and pmap. Okay, those are the main topics for today. So my main point is to get you to understand the difference between map, map2, and pmap. Okay, so map2, we saw a preview of this already, but it works like this, right? We have one vector here, which is this orange vector. We have a different vector here, which is a blue vector. And then we have some function we're going to apply to it. Okay. If we want to, we can also pass an additional stuff here. And that additional stuff will get passed as additional arguments to the function. So for instance, I could loop through one column and a second column and say, give me the mean of column 1 and column 2, like column 1 plus column 2 together, and then give me the mean of that or something. And then here I could say na.rm equals true, okay, to remove missing data or whatever. When you do this, this is the code that you'll write. It expands to something more like this. So you have whatever function you're applying, and the first two arguments to it are going to be the first two elements of the vectors, okay? And then if you pass any additional arguments, those will get passed after, okay? So notice these two are here, and then these two are here, these two are here. But the yellow, the additional arguments that you pass, that's constant across all of them, okay? Just like the function is constant across all of them, okay? So we're going to do a few examples. We're going to go back to that sort of simulation example that I had, but now we're going to make it a little more complicated. So we're iterating over two vectors, okay? We'll also do some plots where we're plotting across two things. Okay, so we're going to simulate data from a normal distribution again. Just like before, we're going to vary the sample size, the n, from 5 to 150 in increments of 5, okay? But we're also going to vary the mean, or mu, for each of the sample sizes from -2 to +2 by increments of 0.25, okay? My kitty is waking up. There he is. All right, I'll put him down. Okay, so how do we get all possible combinations? All right, one way that we can sort of start this is using this function expand.grid. Okay, and expand.grid is like a general function that says, here's one vector, here's another vector, give me all possible combinations of those things. So you can actually pass it more than two vectors. You could give it 3 or 4 or 5, and it'll find all pairwise comparisons. Okay, but here's a really quick example. I create some object I'm calling ints, and another one I'm calling lets. And ints is just 1 to 3, and lets is ABC. Okay, letters. If I call expand.grid on ints and lets, it goes like this, right? 1, 2, 3 for A, 1, 2, 3 for B, and 1, 2, 3 for C. Okay? So please follow along for this section. We're going to use expand.grid to set our sort of conditions for the simulation. Okay? So I'm going to say expand.grid, n is equal to a sequence from 5 to 150 by 5. Mu is going to be a sequence from -2 to 2 by 0.25. So those are the conditions I had outlined on the previous slide. Notice I am naming these things in this instance. And the reason is because now that ends up being the column names here. Back here, I didn't actually name these things. And so I just got var1 and var2. But I probably want them to actually be named. Okay? While you do that, I'll be right back. Okay. So now we want to simulate. Okay, so I can use map2, and I say conditions $n, right? That's going to give me my first vector. And conditions $mu, that's going to be my second. And then I'm going to simulate, so I'm going to say R norm, where n is equal to .x, and mean is equal to .y. Okay, so .x is going to be the placeholder for the first vector that you pass it, and .y is going to be the placeholder for the second vector that you pass it. Okay, and then I'm just setting the standard deviation in this case to 10, but you could set it to whatever, it doesn't really matter. But the standard deviation is constant, and the x, or the n and the mean are being varied. Okay, so we get this list of 510 in return that has all of these. And that 510 is going to be just exactly this, right? 5, 10, 15, 20 for -2, and then 125, 130 for 2 all the way at the bottom, right? So it's all possible combinations. More powerful, I think, is to actually just go ahead and add this list column as a new column, or add this list as a new column to your data frame. Okay, so I have conditions. I'm calling this sim2 now, and I'm going to pipe that to as underscore tibble. That's not actually necessary, but it is quite helpful because tibbles display list columns more nicely than data frames. Okay, then from there, I'm going to mutate and say sim. So I have a new column here called sim is equal to map2. I'm going to loop through n and mu and apply the rnorm function just like I did before. N is equal to dot x, y, or mean is equal to dot y. Okay, so the columns I'm looping through are now the columns of the data frame. And so now I have a list column like this. Does that make sense? Okay, from there, I could then unnest the data frame. So I'm mutating it. And when I say unnest sim, now I have a data frame that looks like this, right? So I have the conditions over here to the left, the n and the mu. And then I have my simulated data after that. So now I have 39,525 rows of simulated data that has all the conditions that I wanted. Okay? All right. So challenge, can you replicate what we just did, but using a row-wise approach? Give that a try. Okay, give me a thumbs up emoji if you were successful. Good. 4 more people than before. Okay, so here's how I would do it. All right, we have row wise, so we take conditions, we pass it to row wise. We say mutate, create a new column called sim, and then we're gonna do our norm with n, mu, and standard deviation equal to 10. But I have to wrap that in list because the return each time is more than 1, right? So then I pipe that to unnest sim, and I end up with the data frame just like we had before. Okay, any questions on that? Okay. All right, let's say we wanted to vary the standard deviation also. Okay. In that case, we would use pmap, or we would use row-wise, which row-wise is nice because if we don't have to worry about things like that too much. But we'll get to pmap here in just a little bit, okay? Let's now do a similar sort of thing where we're creating a bunch of plots, but we're going to vary the title of the plot. Okay, so every plot we produce is going to have a different title. All right, so again, please follow along. We're going to load the 538 data, and then we're going to use the Pulitzer data. So if you don't have 538 installed, I think you all should from last class, but just in case you don't, just do install.packages 538 first, and then you should have it. Okay. Once you have that, go ahead and copy this code, and we're going to create data that looks like this. Okay, so as you're doing that, I'll sort of walk through what this code is doing, right? So we're going to select just the newspaper and any column that starts with num. From there, we're going to pivot longer, and I'm saying minus newspaper, so I'm saying gather, grab all the columns except newspaper to include in the pivot longer. I'm going to put the names, so the old names are going to go to a new column called year range, and the values are going to go to n. Okay, the name prefix is num finals, so this is this is something that's in each column, right? And I'm just going to basically drop that as we pivot longer. Then I'm going to say mutate year range. We're going to string replace all. So in that year range column, I'm going to replace all of the underscores with dashes. Okay? And then finally, I'm going to filter where year range does not equal 1990 to 2014. And the reason for that is because we have 2 separate ones that are for different ranges. So that's like the entire range versus we have 2 separate ranges. Okay, so we end up like this. Here's USA Today. We have the year range, 1990 to 2003, and then the number of Pulitzers. I think this is actually the number of, I'm operating from here on out as if this is the number of Pulitzer Prize winners, but I actually think it's the number of finalists because of this. So I think that's just a mistake, but whatever, it doesn't really matter. Okay. Everybody there and ready to go? Okay. All right, let's say we wanted to create one plot. And again, you can just copy this code if you wanted. But this is for the Wall Street Journal. Okay, so I take Pulitzers. I'm going to pass that to filter and say where newspaper is equal to the Wall Street Journal. I've got some weird formatting here with my spaces, but whatever. And then from there, that's going to go to ggplot. I'm going to put n on the x-axis and year range on the y-axis. I'm going to use geom_col to give me a column where I'm going to fill by the n. So basically, the color of these columns is going to correspond to the x-axis. Okay, so it's just like sort of a double encoding that I've got going on. I'm saying scale field distiller, where the type is sequential. The limits go from 0 to whatever the max of Pulitzers is. Palette is this blue-purple palette, and the direction is 1. Right, so this is kind of complicated to make a color scale, but whatever. And then scale x continuous, the limits are going to go from 0 to the max of Pulitzers, and this is pretty important, as we'll see in a minute. And then I'm going to expand 0, 0 to shove these labels a little bit closer. Guides fill equals none is going to drop the legend, and then I'm adding some labels here, right? So I'm saying the title is Pulitzer Prize winners, Wall Street Journal. X equals a total number of winners, and Y is nothing, right? Well, there's no reason really to have a label there. So that's the plot that I end up creating. All right, the only thing in here that I think is probably unnecessarily complicated is this part. We could have just done something a little simpler, but I do like that color, so there you go. That's why I did it. All right, so now we're going to nest the data. Okay, so we're going to take Pulitzers, we're going to group by newspaper, and we're going to nest. Okay, so now we have a list column with just the data for each of these newspapers. All right. Okay, now we're going to produce all plots. So you try first. Don't worry about the correct title for right now. So back here, I said Pulitzer Prize winners, Wall Street Journal. Rather than doing that for now, just do Pulitzer Prize winners, okay? And don't worry about the actual newspaper. So go ahead and try to create a plot for every newspaper. All right, give me a thumbs up emoji if you felt like you were successful there. Okay. Looks like not super successful. This is how I would have done it. Okay, so I'm going to group by newspaper, nest, mutate. I'm going to create a new column called plot, where I'm going to map through the data. And then I have used this tilde braces syntax, okay? And you could do that. You could also just use the tilde. Either way, it's fine. I kind of like the braces when I have a lot of code because it sort of breaks out what I'm looping through, okay? So I'm using the braces, and then I'm saying ggplot, right? N year range, blah, blah, blah. All of this is basically the exact same, okay? And that is going to produce a plot for each data, okay?
Hey, Daniel.
Yep.
When I run that, it is telling me, it's asking me if I passed AES to the data argument. I don't know if other people are getting that error too, and it's not running.
I'm getting the same error.
I think actually you should have .x right here, ggplot.x. I don't know why that's not there.
Yeah, that works.
Okay. I must not be evaluating this code, otherwise I would have gotten an error. But yeah, the .x should be right there so that you're saying past this data frame. Okay, yeah, there it is on this slide. Now we're going to add a title. Okay, we're going to change the title here. So what I'm going to do is just, and again, I got some weird formatting here. I'm going to now do map to instead of map. And I'm going to loop through with the data and the newspaper. And then the data part is going to be the exact same as before. But now when I get to my title, I'm going to say glue, although you could also do paste 0 or paste or whatever, and that would be fine. But I'm going to say Pulitzer Prize winners, colon, and then this is how glue works, right? You put the curly braces and then whatever you're going to put insert in there. So curly braces dot y, that's going to put the newspaper name in for each Pulitzer as it's looping through. Okay. So when I look at this now, it ends up looking like this. Here's P, and I have the newspaper, and then the data, and then all of the plots. Okay, so there's 50 plots. And if I look at the first couple of them, they look how I would expect them to look, right? Here's the first one, Pulitzer Prize winners, USA Today. Well, if I come back here, the first one is, yes, USA Today, right? And then we have these very small bars. P plot 2, Wall Street Journal. This is the first plot that we've created. Plot 3, New York Times. We have tons of them, right? Including, it looks like the max score. And then plot 4, we have a lot of them, also Los Angeles Times. And one of the things I mentioned earlier is that this bit of code right here is very important, right? We set the limits to be 0 and the max of Pulitzer N, because that's going to keep the x-axis range constant across all of the plots that we're producing. Okay, so for instance, if we didn't do that, this plot would, its x-axis range would go 0 to like 2 or something like that, maybe even 1, I'm not sure. Whereas this way, now they all go 0 to 60-ish, right? And so when you're looking across plots, you can actually compare them. Okay, challenge. You can probably guess where this is going. Can you reproduce that using the row-wise approach? Okay, I didn't set a timer for you this time, apparently. So I'll just look at my own clock. I'll give you like 2 minutes. Okay. Emoji time. How successful did you feel? Looking for a little more feedback than that. No, one person. Okay. All right. Here's how I would do it. Okay. I have Pulitzer. I'm going to nest by newspaper. And then I'm going to say mutate, where I'm creating a new object here called plot. Again, the plot that I'm getting back is not an atomic, it's not going to be an atomic vector of length 1. So if it's anything other than that, then I have to wrap it in list. So I'm wrapping it in list. And then the nice thing here with this, right, is I now don't have to, I just refer to the column names. So ggplot data, the data thing, right? And then I do everything else is the same, but on the title, I say glue Pulitzer Prize winners newspaper, right? Because that's the column here. All right. And then I get the plot here. Again, if this were me actually, I would probably then immediately pass this to ungroup to operate on it anymore. Does that make sense? Questions on that?
I have a question.
Mm-hmm.
It seems like there's no weird thing that ggplot does when you have rowwise or not. Is that true? Is there anything we should ever look out for if we're trying to plot something that we just did rowwise with?
Not that I am aware of. The only thing is that you just have to wrap it in list.
Okay.
Other than that, I think everything should be just the same. You can refer to your data, and then within your data, you can refer to those things, right? And then if there's anything outside of that, like a different column like this that you want to refer to, you're going to probably just refer to that column that way also. Yeah, I don't think there would be anything different because, so for example, one thing that I could imagine is you have maybe multiple data columns, but I think even then, so like you'd have for different layers, right? So even then, I think you would still pass whatever data you wanted here at the top. And then let's say I had geom call and I wanted to pass a different data to that layer. I'm pretty sure you could just say comma data equals and then a name of a different list column in your data set, and it should just work. Any other questions? Okay, moving on for the next almost 20 minutes. No, 10 minutes. We're going to iterate over n vectors. Okay, so that's where we're going to use pmap. Okay, so pmap works a little bit differently than the rest of them. This shows only with 2, and so it looks exactly like map2. But it's just going to be, you're going to feed it some vectors, and then it's going to apply the function to them. Now, the thing that is different is with map, you pass it a vector, then you pass the function. With map2, you pass it the first vector, and then the second vector, and then the function. All right? The thing that's different with pmap is it doesn't know if you're passing it 3 vectors or 76 vectors. Right? It has no way of knowing. So what you have to do then is pass all of those vectors to it in a list. Okay, so the first argument to pmap is always a list. It's one list, and that list is going to be all the things that you're looping through. So it could end up being a list of lists, right? But the first argument is just going to be one single list that has all the vectors that you're going to loop over, and then you have the function that you're going to apply to all of those. Okay, so going back to our simulation, we're going to vary the n from 150, but from 5 to 150 in increments of 5. Vary the mean from -2 to 2 in increments of 0.25. And then we're going to vary the standard deviation from 1 to 3 in increments of 0.1. Okay, so this is just like we did before. We're going to first set our conditions. Okay, in this case, I've created the data frame. I'm calling it full conditions. Okay, and I'm using expand.grid, specifying the mean, the mu, and the SD to be what we said before, right? And then you can see here's the full conditions. Here it is for 5 to n, this sample size with this mu and this standard deviation. And then finally at the end, sample size varying for this mu and this SD. Okay. Now, to conduct our full simulation, there are a couple of different ways we can do this. All right. So one way is we can actually give it a list like this where we name these things. Okay, I've named this number, average, and stdev. Okay, but this is all to one list that I'm passing to pmap. So again, with pmap, the first argument is always a list of the things that you want to loop through. Okay, so I'm passing it these things. I'm just naming those elements in the list. Then I'm going to apply a function which takes those 3 arguments, okay? And then I'm going to say R norm n is equal to number, this thing, which is going to be this thing, right? Mean is equal to average, which is this thing, which is equal to this thing. And then SD is equal to stdev, which is here, this argument, which is that. Okay? And then I get my full simulation. Now that's, I think, complicated and sometimes can make your code a little bit more clear to actually call out things like that with names. But I think this alternative specification is generally more straightforward. Okay, so just like we can use .x and .y with the tilde, when we're using pmap, we can use the tilde and then we just refer to the index of the list. Okay, so I say ... 1 to refer to this first element of the list that I'm passing, and ... 2 to refer to this second element of the list I'm passing, and ... 3 to refer to the third one. Okay, so this is obviously more compact, but I actually think it's a little more clear what's going on too. And this is the exact same thing as this. Okay, and this is also similar to map, right? We could always say function var and then pass var somewhere in our function. We don't always have to use the tilde and .x. We just do because it's nice and easy, right? And so this is that same sort of tilde syntax with pmap, where instead of using .x and .y, again, pmap, you might have 6 things that you're looping over, right? So you could say ... 1, ... 2, ... 3, ... 4, ... 5, etc. Okay, and that gives you the exact same thing. This one is even simpler, but it's maybe a little too clever because data frames are a list, right? I can just pass the data frame. It has 3 columns. That's 3 elements of a list. So now I can say rnorm ... 1 to say the first column of the data frame, ... 2 to say the second column of the data frame, and then ... 3 to say the third column of the data frame. Okay, so all 3 of those are the exact same. This one, I think, is probably a little less clear because you're assuming that whoever's reading this code, if it's not you, understands that lists and data frames are the same thing, basically. Okay. All right, and then of course, we could do a list column version. So we have our full conditions, going to pass it to as_tibble. Again, that's not necessary, but it is nice. And then we'll say sim is equal to pmap, where I'm going to say list of the 3 columns, n, mu, sd. And then I'm going to say rnorm ... 1, ... 2, ... 3. I think in this case, actually, we could just say rnorm, and that's it, because those 3 arguments would be passed in the 3 orders, but this might be a little more clear. Okay. And then, of course, we could unnest sim from there. And now we have all of our simulated data, which in this case is 830,000 observations. And it's pretty amazingly fast, right? And keeps us really well organized. Okay. We only have 1 minute left. If you want to try to go ahead and replicate that with NestBy, you can, but I'm going to close out for today, and we will start here on Wednesday. I think we should be able to get through this and probably most of the mapping variant or looping variants on Wednesday, but we may not get through them entirely, but I think we will get close if not. Okay. Any last minute questions before we sign off for the day? Alrighty. Thank you all, and I'll see you Wednesday.